Good morning, students. Today we are going to see the topic distributed system deadlock. So let me say about deadlock. A deadlock is a situation where a system processes are blocked because each process is holding a resource and waiting for another resource occupied by some other process. When the situation arises, we can call it as deadlock. Okay, so definitely when we talk about this deadlock, it definitely happen in the distributed system because the distributed system is a vast one, right? So many networks, so many components are distributed and they are all independent components. So they connected with the help of messages. So there is a heavy chance of getting deadlock. Okay, and deadlock detection only a possible solution. So we need to detect the deadlock and we have to do some effective measures to avoid it. Okay, so when we talk about this deadlock detection, we have to consider two parameters. One is progress and another one is safety. So progress in the sense the method should be able to detect all the deadlocks in the system, whereas safety in the sense the method should not detect false or phantom deadlocks. Okay, and when we plan to detect this deadlock, we have three major approach. One is a centralized approach, another one is a distributed approach, and one more thing, that is hierarchical approach. So we'll see one by one. Centralized approach. So the centralized approach, here there is only one responsible resource to detect deadlock. The advantage of this approach is that it is simple and easy to implement, while the drawbacks include excessive workload at one node, single point of failure, which in turn make the system less reliable. Yeah, definitely that coordinated node is failed means the entire system will get collapsed, right? So that is a major disadvantage when we talk about the centralized approach. Then distributed approach. In the distributed approach, different modes work together to detect deadlocks. No single point failures as workload is equally divided among all nodes. So here all nodes are treated equally. The speed of deadlock detection also increases because we are not focusing on the centralized node. So we can easily detect when compared to this centralized approach. Third one is hierarchical approach. This approach is the most advantage approach because it is a combination of both centralized and distributed approach of deadlock detection in the distributed system. In this approach, some selected nodes or cluster of nodes are responsible for deadlock detection. Instead of having only one node, we are having a cluster of nodes. They can able to detect the deadlock, and these selected nodes are normally controlled by a single node. Okay. Then another important thing is whenever we generate algorithm, we need to have some preconditions. So we are thinking that we have a reusable resources. Only one copy of each resource is available, and process can be in two state, that is running and block state. And these are the things we are assuming, and we are using a wait for graph in order to detect the deadlock. Okay, so a graph is drawn based on the request and acquirement of the resource. If the graph created has a closed loop or cycle, then there is a chance of having deadlock. So that is a usage of using wait for graph. Okay, then so actually several deadlock handling strategies are available. Handling of deadlock become highly complicated in distributed system because no site has accurate knowledge of the current state of the system, and because every inter-site communication involve a finite and unpredictable delay. There are three strategies we can use for handling the deadlock. First one is deadlock prevention, deadlock avoidance, and third one is deadlock detection. So deadlock prevention, this is achieved either by having a process acquire all the needed resources simultaneously before it begins executing, or by preempting a process which holds the needed resources. This approach is highly inefficient and impractical in distributed system. And the deadlock avoidance, a resource is granted to a process if the resulting global system state is safe. This is impractical again in distributed system. But deadlock detection, this requires examination of the status of process resource interaction for presence of cyclic wait. This can be acceptable in case of distributed system. Okay, so this is the best approach to handle deadlock in distributed system because we can easily detect it. Now, two issues in deadlock detection is there. So the two major issues are detection of existing deadlock and resolution of detected deadlocks. So deadlock detection involves addressing two issues, namely maintenance of the wait for graph and stretching of the wait for graph for the presence of cycles or not. Because we are drawing the graph or we are plotting the graph and we are finding if there is any cycle mean, there is a heavy chance of having deadlock. Okay, then correctness criteria. A deadlock detection algorithm must satisfy the following condition, that is progress and safety. So progress in the sense no undetected deadlocks. The algorithm must detect all existing deadlocks in finite time. In other words, after all wait for dependencies for a deadlock have formed, the algorithm should not wait for any more events to occur to detect the deadlock. Safety. No false deadlocks. The algorithm should not report deadlocks which do not exist. That is very, very important, isn't it? So wrong assumption or wrong broadcasting of wrong message is vulnerable. This is also called as phantom or false deadlocks. Okay. Next one is resolution of detected deadlock. Deadlock resolution involves breaking existing wait for dependencies between the processes to resolve the deadlock. It involves rolling back one or more deadlocked processes and assigning their resources to blocked processes so that they can resume execution. Deadlock detection algorithm propagate information regarding wait for dependencies along the edges of the wait for graph. So that can be very helpful because when a third party or a third party node just seeing this message, they can able to see the dependency features of a particular resource as well as node. When a wait for dependency is broken, the corresponding information should be immediately cleaned from the system. If this information is not cleaned in a timely manner, it may result in a detection of random deadlock. So that is very important. Next, models of deadlock. The models of deadlocks are explained based on their hierarchy. The diagram illustrates the working of the deadlock model. So we can say that there are passive processes that are already acquired the resources and active processes, they are waiting for resources. So we have two processes, right? Either it will wait for the resource, or some process they already have the resource in their hands. Okay, so several models are there: ANT model, OR model, P out of Q model, and unrestricted models. Okay, so we will see what is in the ANT model. So from the name itself, in the ANT model, a passive process becomes active only after a message from each process in its dependent set has arrived. Okay, so a process can request more than one resource simultaneously, and the request is satisfied only after all the requested resources are granted to the process. The requested resources may exist at a different location. Okay, and the out degree of a node in the work from graph for ANT model can be more than one. Okay. So these are the some points, and each node of the work from wait for graph is in such a model is called an ANT. Okay. So the next model before going this. Again, here also we are drawing the wait for graph and we are detecting the cycle. We can say that there is a deadlock. R model, a process can make a request for numerous resources simultaneously and the request is satisfied if any one of the requested resources is granted. Presence of a cycle in the wait for graph of an OR model does not imply a deadlock in the OR model or OR model. In the OR model, the presence of a knot indicates a deadlock. Again, if there is a cycle, we can say that it's a deadlock. Okay. Then P out of Q model. This is a variation of AND OR model. So it's a combination of AND and OR model. This allows a request to obtain any K variable resources from a pool of N resources. Both the models are same in expressive power. Each request in the model can be expressed in the AND OR model and vice versa. Okay. The last model is unrestricted model. From the name itself, there is no assumptions are made regarding the underlying structure of resource request. In this model, only one assumption that the deadlock is stable is made, and hence it is the most general model. It helps separate concerns about properties of the problem like stability and deadlock are separated from underlying distributed system computation like message passing versus synchronous communication. Okay, so that's all about various models of deadlock. Thank you for listening. Thank you.